In a previous episode, I showed you how to use SPI from the Raspberry Pi Pico in order to talk to a sensor. I'm going to build on that concept and show you how to use SPI to talk to an SD card so you can read and write data for long-term storage. This is great for things like data loggers, and I'm going to show you how to do this using MicroPython and C. Let's get started. SD stands for Secure Digital, and it's an evolution of the old multimedia cards, or MMCs. This is a micro SD card, which is smaller than a regular SD card, but it's capable of holding gigabytes of data. SD has its own protocol that uses a 4-bit wide bus labeled DAT0 through DAT3. While this is faster than SPI, it's more complicated to use, which is why we're going to stick with the simpler SPI protocol for now. To use SPI, we leave DAT1 and DAT2 unconnected. DAT3 is chip select. Command is data in, or MOSI. Clock is the clock line, and DAT0 is data out, or MISO. We'll also need to send a sequence of special commands to the card to put it into SPI mode, but the libraries we use will do that for us. The libraries I'm going to show you rely on the SPI protocol to communicate with the SD card. Lucky for us, the RP2040 has a built-in SPI peripheral. However, I imagine you could program some PIO instances that are in the RP2040 to communicate with the faster SD protocol. But for now, let's go with the easier route and use SPI. Here's how I connected the SD card breakout board to my Pico. Notice that this Adafruit board lets you use the SD interface, or SPI. I connect 3.3 volts out from the Pico to the 3-volt pin on the board and connect the ground lines together. I'll use the SPI1 instance in the RP2040 for this operation. I connect SCK to CLK, RX or MISO to serial out. TX or MOSI goes to serial in. We could probably use any GPIO for the chip select line, but I'll use the SPI1 CS pin attached to GP9. MicroPython has some built-in libraries for working with SD cards and file systems. The Pico version of MicroPython, known as the RP2 port, supports LittleFS and FatFS out of the box. LittleFS was created specifically for embedded projects. The libraries are usually smaller than FAT, and it's resistant to corruption on power loss. With FAT, you can often corrupt the whole drive if you disconnect power before finishing a write. However, I've read that LittleFS may still have some bugs as it's relatively new, so use it at your own risk. FAT is tried and true, so let's go with that for now. Most modern operating systems also recognize FAT out of the box, so we don't need to install any special software. Before we write our program, we'll need to format the SD card. I've had the best luck with name brand SD cards in the 1 to 8 gigabyte range, but your results may vary. Insert the card into your computer using a reader and use whatever formatting tool you have available, or download one if you need. Format the card as FAT32. I recommend starting with a small block size like 512 or 1024 bytes to start. Feel free to try increasing this later. When it's done formatting, make sure you eject the card. This is especially important on Windows. Insert the card into your breakout board. Put your Pico into bootloader mode by holding the boot select button while plugging in the USB cable. In Thonny, make sure that the Raspberry Pi Pico is selected as your board. Click Configure Interpreter and click Install or Update Firmware. Make sure you are running at least version 1.15, as that's the version where they enabled FatFS for the Pico in MicroPython. If not, click the Install button to download and install the latest MicroPython onto your Pico. Head to github.com/MicroPython/MicroPython, which is the official MicroPython repository. While MicroPython supports FAT out of the box, we still need the library that allows us to communicate with the SD card on a low level. Head to Drivers, SD card, and sdcard.py. Click Raw, select all of the code, and copy it. Back in Thonny, start a new file and paste in the SD card code. Click File, Save As, and choose to save the file on the Pico. Create a new folder named lib. In that folder, save the file as sdcard.py. In a new program, import machine, SD card, and UOS libraries. Make pin 9 our chip select pin and configure the SPI port just as we did in the SPI episode. However, this time we're using SPI interface 1 instead of 0. I'll keep the baud rate at 1 MHz, but feel free to play with this to see if you can get reading and writing to be faster. I'll set the polarity and phase both to 0 and assign the SPI pins. Next, we create the SD card object and pass it our SPI interface and CS pin. Then we use UOS to mount the FAT file system. We'll mount it to /SD. From there, we can read and write to files just like we would in regular Python. Note that the path to the file is /SD/filename, so I'll create a file named text01.txt in the SD root directory. I'll write a couple of lines to that file and then close it. Then I'll open the file in read mode and print out the lines we just wrote. I recommend saving this program to your computer somewhere so you don't lose it. I'll name it sd_fat_spy.py. Then run it on your Pico. If all goes well, you should see the contents of the newly created file printed to the console. Now, let's do the same thing using the C SDK. This process is a little more involved and will need to include a third-party library to make it all work. Copy the Blink project we started with and rename the folder to something like sd_fat_spy. Go into that directory and delete the build folder. In VS Code, go to File and Open Folder. Open the project folder that you just created. Open a new terminal, which should put you in the project directory to start. If you're on Windows, you'll want to make sure that this is git bash or something that has access to the git command. From there, create a new folder named lib. Navigate into that folder and enter git clone https://github.com/carl-k3/no-os-fat-fs-sd-spy-rpi-pico.git. This will download the third-party library for us to use. Open CMake-lists and change the project name to something like sd_fat_spy. Add the add_subdirectory function after your add_executable call. Set the source parameter to the location of the fatfs spy folder in the library we just downloaded and tell it to output to the build directory. You'll also want to add fatfs spy to the target link libraries function so that the library gets linked after it's built. Finally, enable the UART output if you're using Pico Probe for debugging or the USB output if not. Save this file and run CMake if it doesn't run automatically. If you have the CMake extension installed, you might have to select the ARM GCC toolkit and set the build configuration to debug. Go into the SD driver directory in lib, fatfs spy, SD driver, and open hwconfig.c. Near the top, change the SPY settings to match the one for our chosen SPY port. This means switching to SPY 1 and setting MISO to pin 8, MOSI to pin 11, and SCK to pin 10. I recommend starting with a slower clock speed, like 1 MHz, just to make sure things work. Feel free to try increasing this later. The other variables get updated automatically in the program, so we don't need to touch them. In SD cards, note the name of the mounted device, which should be 0:. Change the SSGPIO variable to our chosen chip select pin, which is pin 9. We're not using the card detect line, so change card detected true to -1. Save this file. Then open main.c. We don't need anything in here to start, so let's delete all of it. At the top, include stdio, stdlib, as well as SD card and ff from the new library. In main, create some variables to work with our SD card and file system. fresult, fatfs, and fill are all from the fatfs library. We'll also need a buffer for holding data and a file name string. As we've done in previous episodes, initialize the serial port and print something out to the console as a test. I'll add a section here so that the user has to press enter to start the test. This is so you don't miss any serial output when you run the program. Then we call the SD-init driver function to initialize the SD card driver. This will return true if it works, so if it fails, we'll print an error message and hang the processor. Then we use the FATFS library to mount the file system on the SD card. Note that the name of the file system must match the one we set in the config file, which is 0: for me. Next, we open the file for writing using the FA-write flag ORed with the FA-create-always flag. These arguments will create the file if it doesn't exist. If it does exist, everything in the file will be deleted, so be careful with these arguments. Then we'll write a couple of lines to the file using fprintf. You'll always want to close the file after using it, so I'll show that here. Just as a test, we'll open the file back up for reading this time. We'll use fgits to print out everything in the file to the console before we close it again with fclose. Finally, we'll unmount the drive when we're done using it and tell the processor to sleep forever. Use make to build your program. If you're using Pico Probe and the debug extension, you can simply click on Start Debugging to run the program, but I'll show you how to run it with the .uf2 file. The FATFS module for working with FAT on embedded systems was written by Chan, and it's incredibly popular in the embedded community. If you head to elmchan.org, you can go to Softwares and FATFS module to see the API documentation for working with it. The library we downloaded includes this library as a submodule, so if you want to know how to work with files, I recommend looking at this documentation. When the build process is done, it should put a .uf2 file into the build directory. Put your Pico into bootloader mode and it should enumerate as a mass storage device on your computer. Navigate into the build directory of your project and copy the .uf2 file. Go into the rpi-rp2 drive and paste it in the top level directory. When it's done copying, open a serial terminal to the Pico. We'll probably miss the first message, but just press enter to run the rest of the program. You should see the contents of the file we just created printed out to the console. Let's check to make sure that this all really worked. Remove the SD card from your project and put it into a reader attached to your computer. Open the SD card drive and you should see two files. The first was created with the MicroPython demo and the second was created with the C SDK demo. Feel free to open them and examine the contents. They should match what we wrote in code. Writing to files on an SD card is a great way to record events or log data from a sensor. I hope this has helped you get started using an SD card on your next Pico project. Good luck and happy hacking!